Looked at Punnett squares, but now we're going to be applying them to crossing people with different blood types. So in our first example here, we have a person with type AB blood and a person with type O blood. So we know that these are found on homologous chromosomes. So this allele and this allele, they are on different chromosomes, and we know based on meiosis that only one of the two chromosomes can be passed to a child. So that means we have to segregate these two alleles. We'll put the A right here and the B right here. And the same for this parent, have to segregate them because only one of the two alleles can be passed on. Now we can complete our Punnett square. Just brought my A down and my O down. Now I'm going to bring my A across and my B across. And these are my possible genotypic outcomes for children produced by this parental combination. And I can see that 25% will have the homozygous dominant A genotype, resulting in type A blood. I can see that 25% will have the heterozygous combination for type A blood. 25% will have AB blood, and 25% will have the heterozygous combination for type B blood. So when I look at it at this level, I know now that 50% of the offspring will have type A blood, 25% will probably have AB blood, and 25% will have type B blood. Now let's look at a second cross between another parent who's AB and another parent who is type A but has a different genotype. Will they have the same outcome? You're probably starting to see that no, they won't. But let's take a look at how they compare. Again, we have to segregate our alleles. And we can fill in our Punnett square. A down, A down, A down, A down, A across, B across, and across. Now I can see that 50% of my children will be expected to have the homozygous A combination and the A phenotype, type A blood, and 50% will be expected to have type AB blood. So we do have different outcomes even though the parental combinations have the exact same blood type. The genotype matters. Let's do one more just for good measure. Let's cross a person who is type B blood and a person that's type O blood. Both are heterozygous for their trait. So again, we'll segregate our alleles. Bring our A down and down, our O down, our B across, and our O across. Now here we have 25% that are AB blood, 25% that would be expected to have type B blood, but the heterozygous genotype. 25% would be expected to have type A blood, but have the heterozygous genotype, and 25% would be expected to be type O and have the homozygous recessive genotype. So again, these parental combinations down here would produce 4 different possible genotype outcomes and 4 possible different children with different blood types.